finite space, whatever. Fantastic. Understand. And then you take this group completion. So now you have these cohomology groups here, and you have some actual elements inside these cohomology groups, and you run away with this. You prove Hopf invariant one or something fun like this. Now, the nice thing about having a description of complex K-theory like this is that it's really easy to, okay, now I realize my face is blocking things. Let's put it over there. Okay, is that you can just add a G everywhere and you get a really well-defined equivariant cohomology theory. So I can really just say the G-equivariant K-theory of some finite GCW complex are just G vector bundles on X, and you just group completion. And this definition works totally well if you have any compactly grouped G. In fact, probably a topological group, it works pretty well. And we get a nice definition. We get a nice G-equivariant cohomology theory. So we get a nice G spectrum, which I'll write like this for the rest of the talk. KG inside G spectra. Okay, so we want to do the same sort of thing for elliptic cohomology, but we run into this problem, which is that there is just no geometric interpretation for the elements inside the cohomology groups inside the elliptic cohomology groups of some space. It's not like this is a family of elliptic curves over this space or vector bundles with some weird tangential properties or something like this. We really don't know what, if you have an element inside this group, which we can define, there's just no obvious geometric interpretation for this. So we can't just take a definition and add G's everywhere. We need to somehow rework things. So the first thing I want to do is I want to talk about sort of reworking equivariant K-theory into a form that we can then generalize to elliptic cohomology. Here I just have examples of cohomology theories where we do have a geometric meaning. So for like K-theory of vector bundles, for these Thom spectra, we have sort of framed structured manifolds and stuff like this. And then of course, for singular cohomology, we have like cochains and stuff like this. Okay, so now comes a little bit of the algebraic geometric input. And I'm going to assume that everyone is reasonably familiar with the idea that K-theory has something to do with this multiplicative group scheme, has something to do with the multiplicative formal group law. Maybe you've seen that from your chromatic homotopy theory or complex oriented cohomology theories or something like this. So I just want to define this group scheme. So we all know what this ring is, spec, this ring of this polynomial, Laurent polynomial ring integral. And it's a multiplicative, it's not just a scheme, not just an affine scheme, so spec of a ring, but it's actually a group scheme, which means that the ring comes with the structure of some Hopf algebra. In other words, it comes with some sort of co-multiplication, which you can really write down explicitly. So the co-multiplication looks like this. Here we have the ring on one side, and then we have the tensor product of the ring with itself over here. I'll just write that down. And this co-multiplication is just the thing that sends t to x times y. If you want to sort of unravel your formal group law theory, you can try to see how this group scheme relates to a formal group law. That can be fun. Okay, so now notice the following. Now we want to talk about K-theory, equivariant K-theory, and the group scheme will come back in a second. So equivariant K-theory of a point, by definition, as I wrote above, is just you look at G vector bundles over a point, and then you group complete this monoid. But of course, vector bundles over a point should just be vector spaces over a point with G action. In other words, they're just G representations. So this is the same as rep G. Let's just say over the complex numbers so we don't forget. And then we group complete this. And this is also known as the representation ring of G. And now, if I remember correctly, I've got some examples of some representation rings. So for example, we can look at the equivariant K-theory for U1, so the first unitary group. So I chose to write it as U1, but this is of course the same as S1, it's the same as SO2, all these things. And by definition, or from what I've written here, the U1 equivariant K-theory of the point is just the representation ring of U1. And so now we just need to see how, we just need to understand all the representations for U1. But we know that these are generated by some element T via multiplication, which is going to be the tautological U1 action on C. So you look at the complex numbers with an action by U1 given by the definition of U1 acting on C. And so this irreducible guy generates this polynomial ring, this Laurent polynomial ring here. And now you make the observation that this looks exactly the same as the as this multiplicative group scheme here. It looks exactly the same as the global sections of this multiplicative group scheme. Or, in other words, the spectrum of the U1 equivariant K-theory of a point is exactly this group scheme. And we'll come back to this in a second. I kind of want to play between the U1 story and the Cn story for some cyclic group Cn. Okay, so sometimes it's good having a cold going into a talk because it gives you like a break every now and then to cough. Okay, so like I said, we'll come back to this in 1 second. So now I want to look at the equivariant K-theory of a point, but with respect to the group Cn. Are those ones, not sevens? Yeah, they're ones, sorry. Yeah, my sevens will have a big line through them, but you probably won't see any sevens. So yeah, let's have a look at this equivariant K-theory of a point for Cn. No worries. Well, this is just going to be the representation ring for Cn, and this, in this case, is this ring here. So it's the quotient of the polynomial ring by this relation, where this element tau is now, again, it's this one-dimensional complex representation where the generator of Cn acts by rotation by, I wrote down the number here so I wouldn't forget, 2 pi I on n, it just rotates around there. We're thinking of Cn as a subgroup of U1 here. This is the restricted representation. Okay, so this ring here also has something to do with this multiplicative group scheme. So it turns out that, and I wrote down here that this is a little harder to see, but it's not much harder to see, that the spectrum of the Cn equivariant K-theory of a point is actually what algebraic geometers call UN. And this is the group scheme of nth roots of unity. Okay, and in fact, this group scheme of nth roots of unity is actually canonically a subgroup scheme of GM. We actually write it like this. It's actually the n torsion points inside GM. So I'll write, this is the n torsion inside GM. So I'll draw a little cartoon here. So if you think about GM as being like S1, so a sort of circle like this, then, can I reach a blue? Yep. Then the roots of unity are really just the classical roots of unity of the complex numbers. So for example, this guy would be U6 sitting inside GM. Okay. So what I want to do is I want to sort of manipulate these two formulas for the equivariant K-theory of U1 and the equivariant K-theory of Cn into some sort of form that has something to do with GM, but also obviously has something to do with the group. Like somehow the group U1 vanished in this here, and the group Cn somehow turned into an N. And so one way we can do this is you can realize that the N torsion of a group scheme is the same as the homomorphism group scheme from Cn into that group scheme. So in other words, if you want to pick out an n torsion point in your group scheme, you could also just look at a homomorphism from Cn into your group scheme. I'm saying the word scheme a lot, but if you remove the word scheme, this is pretty clear in the category of abelian groups. Okay, and it turns out that this of course, a little bit more tautologically, this top guy here can also be written in terms of some sort of homomorphism scheme. This is just the HOM scheme from Z into GM. Because, of course, what is a point in GM? It's just a choice of homomorphism from Z into GM. I mean, Z is the free abelian group on a single generator. So this is sort of tautological. And so you can see this formula here for, again, the CN equivariant K-theory of a point has something to do with CN and something to do with GM. But when we look upstairs at U1, we have GM appearing all of a sudden, but we have Z instead of U1. And now you do this little sleight of hand, which I'm amazed that it works, and I like understand why it's necessary, but I still find it kind of sneaky, is you realize that Z is actually the Pontryagin dual of U1. So here, this is Pontryagin dual. So this is just HOM from G into U1 itself. So in other words, we know that maps from U1 to U1, maps from a circle to a circle are just Z. I mean, this is the pi1 of S1 calculation. And you can do something very similar down here because Cn is Pontryagin self-dual. So this is HOM from Cn dual into GM. Okay, so I've sort of manipulated these formulas enough. I know it's very sneaky. I find it surprising. So now, is there a question?
Yeah, sorry, I'm confused. So you somehow say that this case is more than a Hopf structure, right? Otherwise, I wouldn't find them.
I'm sorry, it's a bit hard to hear. So it's something about the HOM schemes?
Yeah, and your K-theory, you seem to think that it has a Hopf structure, right?
I'm still finding it hard. Sorry.
I'm just trying your structures because you stressed that you are considering group schemes. So somehow you're considering this group structure.
I'm sorry, the microphone is pretty bad. Maybe you could type that question in chat. Okay, I'll wait for that to pop up. Sorry about that. Okay, so yeah, we now have kind of a uniform description for what spec of this K-theory is. We just take HOM, we take the group we want, we take its Pontryagin dual, and we chuck GM there. What Hopf structure on K-theory are we taking? Yeah. Good question. This is an identification of HOM schemes, and we're taking a sort of Hopf algebra structure which is coming from this equivariance here. I can talk about that more at the end. Like we're sort of using the diagonal map coming from the restriction maps from U1. I can write it down at the end if you like, but good question. Yeah, this is an isomorphism of group schemes. Okay, so yeah, we have this uniform description for spec of K-theory of equivariant K-theory. And it turns out that this is actually true in a lot of generality. So it turns out that spec of G-equivariant K-theory of a point is exactly the same. Oh, now I can use my highlighter. Is exactly the same as this homomorphism group scheme from the Pontryagin dual of G into GM. And this actually holds for all abelian compact Lie groups G. In fact, proving it for all abelian compact Lie groups G is essentially boiling it down to these two cases and making sure that things behave well with respect to products and stuff like that. Okay, so that's pretty neat. And in fact, this statement, everything I've been saying so far is very discrete, but it actually holds spectrally too. So actually, there's an isomorphism here of spectral group schemes. I'll just write spectral schemes for now, where now we're looking at spec of an E infinity ring. So this will be the G fixed points of K-theory. And here we have HOM. Oh, excuse me. This is now the HOM group scheme, again, in the category of spectral schemes over this E infinity ring K. And this is pretty remarkable. That this isomorphism lifts from a discrete thing to a very spectral thing. And so this is going to be our inspiration going forward. This is sort of what we'll take as our definition. We're going to just replace this guy here, this multiplicative group scheme over K with some other derived abelian group scheme over some E infinity ring. And then we're just going to run with that. Okay, are there any other questions now? We're going to move on to the next section shortly. Okay, nice. Cool. Well, now I can just give you the construction. And I mean, I've already given this to you. So if you want to, at home, write down what you think the definition using this inspiration is, then you'll probably get it pretty right. But you'll see it in a second. I just want to go through what an elliptic curve is quickly, because for a homotopy theoretic audience. So we want to work with an elliptic curve over, so an elliptic curve C over an E infinity ring R. So what is this going to be? Well, we're going to work in spectral algebraic geometry. So we're going to look at regular algebraic geometry where we have commutative rings everywhere, and we have schemes which are sort of topologically, they're ringed spaces which locally look like affine schemes. And we're going to construct some sort of, we're going to do this whole story, this whole topologically this whole ringed spaces story, but now for ringed, spectrally ringed spaces. And we get a whole story for spectral schemes and spectral stacks and stuff like that, where we've replaced the discrete rings downstairs with E infinity rings. And so an elliptic curve over an E infinity ring is just going to be some sort of spectral abelian group scheme. So spectral just means it's now in our world. And abelian group scheme is now what you can guess it is. You can define abelian group objects in any infinity category with finite products. So it's an abelian group scheme C with a map to spec of R. And then you ask for all these algebrogeometric criteria, which you usually like from things that behave well. So you want it to be flat, proper, smooth. You just want it to be a nice smooth curve that lives over spec of R. So I can draw a little cartoon for you maybe. And then you ask for these extra conditions, like you say, for each map from your E infinity ring to a discrete ring, you ask that the base change of this spectral gadget actually turns out to be a classic elliptic curve. So some zero locus of some sort of cubic equation like this. Great question about connectivity. So R doesn't have to be connective, but again, this is a very sneaky move. You define an elliptic curve over a non-connective E infinity ring as an elliptic curve over its connective cover. Yeah, that's a little bit sneaky, but this is what Lurie does in elliptic 1, 2, and 3, and it seems to work very well, despite being very sneaky. Okay, so what is this? Well, if you imagine spec R being something like this, you sort of have your family of prime ideals as they move, then your elliptic curve is going to be some sort of one-dimensional curve that lives over this, such that at every point you have an elliptic curve. So classically, they look something like this. Woo. Sometimes they also look like this. You can go on Wikipedia and look at some nice pictures, or just Google it. And you should also remember that if you're working over C, maybe I'll make a little bit of room here for a second. If you're working over the complex numbers, then all elliptic curves look like a torus. So they look like S1 cross S1, with the group structure really coming from S1 cross S1. So you really think about this as like the complex numbers modulo some lattice. So if you want to keep in mind an elliptic curve is somehow a torus defined over a general ring or a scheme or an E infinity ring, then I think this intuition is really helpful. Okay, so now we've got our definition for equivariant elliptic cohomology. It just jumps right out at us. If we have an elliptic curve C over some E infinity ring R, then we can just literally define the elliptic cohomology of G, the G-equivariant elliptic cohomology of C over R, just as HOM in the category of R schemes from G dual into C. And we're going to make this definition for every abelian compact Lie group. So just like in a K-theory case, we really only want to make this definition in the abelian case. Okay, so now you've seen the definition. If you're, I mean, that's an achievement. Now we've seen the definition is sitting right there, and you can honestly say that it's come up in your life. That's nice. I was happy when I first saw this too. Okay, so, and you want to think about this collection of group schemes, or more accurately, maybe its collection of global sections as G varies over all compact abelian Lie groups, as this collection of E-infinity rings, as I've written here, it acts like the G fixed points of a multiplicative equivariant cohomology theory. So if you look in the Gepner-Meyer paper, they actually make this really precise, where they really write this down, and they prove that these global sections actually do define a G-equivariant cohomology theory, at least when G is, do they do it for abelian or for tori? Either one or the other. And for those equivariant homotopy theorists in the audience, I've put the word naive and genuine here. So the multiplicative structure that you get on these cohomology theories is a priori like the weakest form of E-infinity, so just E-infinity in a higher categorical sense without any parameterization over Orbi spaces, over orb or something like this. But it should be genuine in the strongest sense. So it should really define an element in sort of genuine G spectra. It's not just an element in SPBG. Okay. And I've got a few notes here that I just wanted to read out because I think this is nice for the capable homotopy theory audience that I have here. You can extend this definition to all compact Lie groups. Because, I mean, complex K-theory is defined, equivariant complex K-theory is defined for all compact Lie groups. But to do that, you need to talk about pre-orientations. You somehow need to talk about how functorial is this definition in the compact Lie group here. And you want to choose a really special category G to define that, where G lives in, and you want to check that this definition is functorial in this special category. And then you want to start taking Kahn extensions and stuff like this. And the buzzword for this special category is Orbi spaces. So this is, as I mentioned at the beginning, all of this more technical stuff is explained really well in both of the introductions to elliptic cohomology 3 and the Gepner-Meyer equivariant topological modular forms paper. And when I say pre-orientations or orientations, these are very much related to sort of complex orientations that you might see in chromatic homotopy theory. So in a second, we're going to see sort of this derived moduli of elliptic curves with a given orientation. And this is really the thing that comes from chromatic homotopy theory. Another thing I wanted to super quickly mention is that if you know what a derived scheme is, or you know what a derived stack is, then you know how to define these sorts of E-infinity rings here, replacing this R with some scheme or some stack. You just need to write down an atlas for your scheme or stack as some sort of Étale or Zariski hypercover, and then define these geometric fixed point, these global sections here really as just being a limit over all the affine pieces. Of course, when I say a limit over affine pieces, I need to say where this limit is taking place, but if you do it in E-infinity rings, then you're in the right place. So for those of you who know what a derived stack is or have worked with derived schemes before, the generalization is really natural. But I won't go into it too much here, except to say that there is a universal elliptic cohomology theory. So there is a moduli stack of elliptic curves, and we want to work with oriented elliptic curves because then we get sort of all of these nice properties. Yeah, and we can feed this moduli stack of elliptic curves. It, of course, comes with a tautological elliptic curve living over it, the universal elliptic curve, or the universal oriented elliptic curve. And we can now just define equivariant TMF. So I'll write it like this. just as the global sections of HOM now over this moduli stack of G dual, again, going into M uni or. And again, let's take G to be abelian compactly. Okay, cool. I like writing down these definitions and I like seeing them written down. Very nice. Are there any other questions at the moment? Okay, nice. Then I just want to talk about some consequences. They're not going to be obvious consequences. These consequences are concentrated in these aforementioned papers by Lennart, David, and Jacob. And they can be quite involved, but they sort of illustrate that this theory that we've defined here is well behaved. And we often justify, how to view GV as a spectral object. So you really, okay, let me answer these two questions in order. So how to view GV as a spectral object, that's fine. So let's take G to be some abelian group for now, some finite abelian group. Then you can always base change this into any category into abelian objects in any category. In other words, sort of abelian objects in any category are enriched over abelian objects, or let's say tensored over abelian objects in spaces, and then you can just shove in your abelian object in spaces here. So that's how we view that. And the target in this case for TMF is you put in the universal elliptic curve, which lives over this moduli of elliptic curves. No worries. Okay. Cool. So let's move on with, let's do the facts and fun. I'm sorry, I've been very inconsistent with my coloring in terms of what the colors mean, but I just want to move between them in as pretty a way as possible. Okay. So first, I want to mention some similarities between this equivariant elliptic cohomology and equivariant K-theory. The first thing to say is that, let's just restrict to finite abelian groups for now, because maybe I'll mention it later. There are some technical hypotheses we need to move between finite abelian and compact Lie, but we'll get to that later. So let's just take a finite abelian group G. Then we always have some sort of natural comparison map like this, which goes from the G-equivariant elliptic cohomology as defined above to the what I would call sort of Borel equivariant cohomology of the base E infinity ring R. So this R is the same as this R, which the elliptic curve is defined over. And excuse me. And so we have this natural comparison map, and there is a theorem due to Lurie, which says that this map up here is some sort of completion map. So it's saying that if you choose your elliptic curve of your E infinity ring to be oriented, so oriented in the sense that I mentioned above, which I didn't define, it's some sort of something to do with complex orientations, roughly. So if you have an oriented elliptic curve over your E infinity ring, then this map gamma, this comparison map, is actually the completion map of a certain ideal sitting inside pi 0 of R. In other words, this is really a Thiers-Siegel completion theorem. I think that's what I wrote. Yeah. And again, this is a super useful fact, because the thing on the left, this global sections of this equivariant elliptic cohomology theory, should be some sort of finite object. We'll actually see that later on. It should be something that's not too big. It should be finitely generated as a module over R, whereas the thing on the right, I mean, due to the nature of being a completion, it's going to be some huge infinite dimensional thing, which of course, you know, is not the worst thing in the world, but for computational purposes, it's often super nice to have a finite refinement of your infinitely generated guy. And in this case, it's given in a very precise way. It's really saying that this more naive equivariant cohomology theory is really some sort of controllable completion of this nicer theory here. So like I said, this is an Atiyah-Siegel completion theorem, which holds if you replace elliptic cohomology with K-theory. This is the famous Atiyah-Siegel completion theorem. And I wanted to mention here, which in all honesty, I only wrote a few minutes before we started, but elliptic cohomology 3 has so much more than this. So there's not just this kind of Atiyah-Siegel completion theorem, but you also have what Lurie calls tempered ambidexterity. So that's something related to, maybe you're used to the ambidexterity you see in the TN local spectra. This is a similar sort of ambidexterity phenomena, but now holds in the equivariant world. So tempered to Lurie means these sorts of cohomology theories defined by this sort of definition. And he proves some sort of ambidexterity theory in this world, but without Tn or Kn localizing. It's a pretty remarkable setting to prove these sorts of ambidexterity results. There's also this fascinating dependence on generators, which that should be dependence. That's okay. Dependence on generators results, which says that you might know a theorem from K-theory, which says that actually equivariant K-theory for any group can be obtained by the equivariant K-theory for all cyclic groups. So it's somehow telling you that equivariant K-theory is defined for cyclic groups and then sort of can't extend it to everything else. And there's something true like this for elliptic cohomology too. It's saying that equivariant elliptic cohomology for all compact Lie groups is actually Khan extended from compact Lie groups with 2 generators. And again, this is something that if you're used to working with elliptic curves and you see a formula like this, it might be a bit intuitive, but it's a very useful theorem to have at hand. I've also written here Chi theory, which I think I mean character theory. And there's also a whole bunch of base change results and all this sort of great stuff. Again, the introduction to elliptic cohomology 3 is really long and it gets more and more technical as you get going, but it's a great introduction to all of these equivariant cohomology theories that come from derived geometry. So one thing I wanted to mention as well, and this is now a difference between equivariant elliptic cohomology and equivariant K-theory, is some size issues. So sometimes this equivariant elliptic cohomology is actually better behaved than K-theory. And here's an example. Equivariant K-theory, I'm sorry, sometimes I put my G down the bottom and sometimes at the top. I hope it's not too confusing. So this equivariant K-theory for some compact Lie group G is not always a small K module. It's not always dualizable. For example, we've actually already seen this. We know that the K-theory of U1 is the same as this global sections of this spectral group scheme over KU, which is just KU adjoin this Laurent polynomial element. And this is infinitely generated as a module over K-theory. Again, I don't want to behave like infinitely generated things are unapproachable, but in particular, it's not dualizable as a module. But this is something that, this is a problem that we don't have in equivariant elliptic cohomology. So this is now a result of Gepner-Meyer. They show that for every abelian compact Lie group, this E infinity ring is actually dualizable as an R module. So, and dualizable in an obvious sense, there exists a dual. So this is giving you some real finiteness conditions on these spectra, these equivariant spectra. It's really telling you that they cannot blow up and be too big. They're really nice and manageable. And in particular, they write down a formula for the U1 equivariant elliptic cohomology, and it turns out to be exactly R plus another copy of R. That's as an R module. I'm actually not sure what the E infinity structure on the left could be in terms of like some square zero extension or something. So as R modules. Yeah. And a corollary that you can draw from this too is that actually this same result holds. So this guy being dualizable as an R module actually holds for all compact Lie groups, which are the product of a torus with some finite group. So to get this, you need to combine this Gepner-Meyer result with a little bit of Jacob's work, plus an argument that Lennart and David make, plus you have to compare their two worlds. You somehow have to make sure that you can use elliptic 3 at the same time as you use the Gepner-Meyer thing, and that involves a little translation. But in particular, I just want to highlight again, these things are not super big. I'm confused. What is the relation between G being dualizable and that being dualizable for every subgroup? How do I compare this with equivariant dualizability? Yeah, I'm not sure. That's a good question. So at the moment, I'm saying something very sort of absolute in some sense. I'm saying sort of we're taking these global sections, we're taking this thing that should be like the G-equivariant fixed points of this equivariant cohomology theory, and we're saying that just as an R modulus is dualizable. I'm not really sure how to phrase this now in terms of being internal to G spectra or something like this. Okay. They're not easily compared in general. Okay, thank you, Sil. Do you commute any types of fixed point? I will get to that, hopefully. Thanks for pushing me a little further. And thanks for the hint, Sil. Okay, so, yeah, and I just wanted to give a quick plausibility argument why something like this might be true. And the reason is that GM just looks a lot different to C. So when you look at elliptic curves living over schemes, you always ask that they're proper smooth curves. So in particular, if you take their complex points or something like this, or the underlying spaces, you actually have a compact thing, a compact space living over your over every point in your scheme R, or in your whatever scheme you're working over. Whereas here, you have something that is not compact. Although I wrote down GM as kind of being like S1, it's better thought of as being something like C star, which is not compact. And you can think of some sort of formula like this as being somehow a refinement of a cohomology calculation for these groups here. Okay, there's good active chat happening. Okay, I'm going to take another sip of water. Are there any other questions or comments or anything? Okay. I'm sure all of the strong equivariant homotopic theorists in the audience are wondering about the precise connection between everything I've been talking about and G spectra. and I'd be happy to talk about this later, or ask questions at the end or anyway through. But the translation is a little bit requires a little bit of explanation. Okay, but since I have 15 minutes now, or no, since I have five or so minutes now, I want to just briefly mention these equivariant multiplicative structures. So I'll go a little bit quick through this, but feel free to ask questions. So by construction, we've got all of these E infinity rings for all compact abelian G. But we could ask if there's more. Like at the moment, there are only E infinity rings at each G fixed point. We can ask if there are somehow E infinity structures or like power operation structures between them. Excuse me. So one way you can ask for this, if you have some sort of equivariant E infinity ring or some collection of E infinity rings as they vary over different compact Lie groups, you can ask if this sort of E infinity structure can be refined to some N infinity structure where you have norms and stuff like this. So I'm using N infinity in terms of Bloomberg-Hill, sorry. So for us, this means if you have a collection of equivariant E infinity rings like this, do there exist norm maps like this in some coherent sense? Do there exist norm maps which refine the usual multiplication? Whenever I talk to people, or whenever people talk to me too, we seem to expect that this equivariant version of TMF should be N infinity in the most coherent sense, but it's not quite clear how to prove this yet. But we do have some evidence that takes us part of the way there, which is we can construct in joint work with Sil and William, we can construct maps like this after taking geometric fixed points. So in particular, we have this, which I haven't been using my highlighter, but I can use it again. So this result is saying that there do exist maps that look like norms, except we've also applied this geometric fixed point functor. And if you use this canonical isomorphism here between the geometric fixed points of a norm and the geometric fixed points of the subgroup, what we're really doing is constructing a whole bunch of maps like this, which we call geometric norms, this should be part of a sort of higher equivariant multiplicative structure on these cohomology theories. Now, I do have a sketch of a proof, but rather than give a full sketch, I just want to mention what these geometric fixed points are. So we know that the G-equivariant TMF is the global sections of some HOM stack like this. And the intuition that you should get from the isotropy separation sequence that defines the geometric fixed points is that the geometric fixed points should somehow be the G-equivariant part, and then you cut out all of the proper subgroup stuff. And that's exactly what ends up happening. So it turns out that this is the same as the global sections of some stack called ING. So the stack not of all homomorphisms from this Pontryagin dual to C, but just of injections. And another way to write this would be, this is the homomorphism stack from the Pontryagin dual to C, where we remove all the closed substacks which come from proper subgroups. Like this. And this is what I would define as the ING stack. And then it's a result of Gepner-Meyer in some upcoming work that this is actually, that this algebraic geometric object and its global sections are a model for the geometric fixed points of this equivariant theory. And so once you have a geometric model or an algebraic geometric thing that describes this equivariant theory, now we just need to construct a map between these moduli stacks. And if there's one thing that I like to do, it's constructing maps between stacks. And so that's something that I wrote down here, but yeah, maybe we can talk about that later and see if there are any questions. But I just want to say quickly is that some applications of these of constructing these geometric norms is that you can use some extra Gauss-Hopkins obstruction theory and you end up with some literal norms for CP. So you end up with some literal norms like this when, let's say, H is the trivial group and G is CP and R is TMF. So you end up with some literal norms for some small groups using some Gauss-Hopkins obstruction theory and a bit of bootstrapping. And you also end up with these geometric norms give you constructions. It gives you a big construction such that when you specialize to K-theory, you get some sort of delocalization of the image of J. And when you restrict to TMF, you get some sort of, again, some delocal, decomplete version of Barron's QN spectra related to approximations of the K2 local sphere. Okay, I think I've said enough random math now. So yeah, I'll take any questions.
Thank you very much. Is there any more questions?
Can you maybe talk a bit about these CP norms? Yeah.
Yeah, sure. So somehow it's done in the more or less obvious way. We have a look. Let me write TMF as R for now. So we want to construct some sort of norms on CP equivariant TMF like this, and we're just going to use the usual sort of fracture square. So here we've got the geometric fixed points of R. Here we have the Tate of R, and here we have the homotopy fixed points of R. And we construct some sort of, in a coherent way, we construct nice norms on this thing. And there is sort of a canonical choice of norms that belongs down here. I mean, all these things are sort of Borel theories, so we just need to define these norms in terms of Borel data. So it's really just infinity structure coming from the underlying guy. But then we need to make sure that the Borel structure here glues with the structure that we construct, and that's where the obstruction theory comes in, and then you pull it back and you get your norms here. Scroll up to the proof sketch. I can scroll up to here. Oh, excuse me. And the reason why we stop at CP is because just the obstruction theory gets out of hand, and somehow everything that we did before the obstruction theory was sort of, done in a nice coherent way using spectral algebraic geometry, and was very lovely and homotopy coherent. And as soon as you sit down and have to write down Gauss-Hopkins obstruction theory that depends on the order of the group or something like this, I mean, you're probably, Jacob is telling you you're doing things wrong. You should come up with a different approach.
Thank you.
Any more questions?
Also, like you have, sorry.
Okay, I was just wondering, you asked this question about the multiplicative structure in terms of this decomposition as R plus R shifted by 1.
Yeah.
You know how to read it off classically? Like if I give you a classical elliptic curve, you also get this formula for global sections, right?
Yeah. That's a good question. I mean, I would expect that it is the somehow this formula is somehow saying this is a sheaf cohomology of the elliptic curve. And I mean, this is square zero because like this, the R plus 1 is the sort of the shift of R is the thing living in degree 1, and that clearly all squares to 0. So I would sort of guess that maybe this is like the trivial square zero extension as an E infinity ring, but I don't know. I don't know how one would sit down and try to figure that out too. Sorry, I'm not even on the right page. Where are we? Here. Yeah, that's right. I don't know. Good question. I'll come down the corridor and talk to you about it still.
Okay. Yes, sir. Just asking about the pre-orientations that you mentioned. And how that's related to chromatic, the complex orientations. So I think.
Yeah. Yeah, I did mention it. I mentioned it because I have some sort of a mathematical integrity, but and I don't want to totally lie to you when I write things down. But yeah, I mean the connection is sort of nebulous. So if you have a look through elliptic cohomology 2, it's titled elliptic cohomology 2 orientations. And there Lurie really talks, especially in chapter 4, he really talks about the connections between having an orientation on your formal group and having choosing an orientation for your, like a complex orientation for your cohomology theory and how these things relate. And choosing an orientation for your elliptic curve, it will be the same as choosing an orientation for the underlying formal group. Is that true? Yeah, I mean, that's part of the definition. Or at least it's the same as choosing I would need to double check that. But these things are related, sort of choosing the orientations for the elliptic curve and the associated formal group. I think they're the same, but at the very least they're related. And it's this interpretation in terms of the orientations and the pre-orientations for the formal group, which is discussed in elliptic 2, which really tells you something like, oh, if you have an orientation for your formal group over an E infinity ring, then in particular, your E infinity ring is complex oriented. And in particular, it has an associated equivalent formal group. And actually the pre-orientation gives you a map from your formal group to your equivalent guy. And the fact that it's an orientation is telling you that this is an isomorphism too.
Sorry, that was chapter 4, right?
Yeah, chapter 4 of elliptic 2.
Yeah, another naive question. I don't know. I asked this question to Mark Behrens actually. So you have this recently there's work by Dexter Chua on C2 equivariant TMF computation, right?
Mm-hmm.
Maybe a computational question, but I was thinking of like the C2 equivariant version, C2 equivariant computations in the 3-law cohort. Like I don't know if I should ask this question, but I don't know.
So I'll say I have read through Dexter's paper, and like it's fantastic that we have an actual computation and more than just a computation, but really like this is the homotopy type written down. That's lovely, but I don't have any. I wish I would have some intuition for sort of like how to take that to CP or something like this, but I mean, one thing that's interesting would be to really look into Dexter's computation and see sort of where the genuinely equivariant power operations would live in his computation and really try to sort of extract something out of that. But that would require really looking at this decomposition he writes down, which is, it's a relatively small complex, but I mean, TMF is a relatively complex guy as well, so.
I was actually supposed to ask this to Sue as well.
Yeah, I see. Yeah, no, I wish I had more to say about that, but yeah.
Thanks. Very tough. Thanks.
Thank you.
Okay, if there's no more questions, I think we should contact Jack or Greg John. This was interesting. Glad I made it in here.
Thank you.